Swayam Prabha. Digital India. Educated India.
Yeah, welcome back. So, today I am going to do the derivation of torque of the induction motor by co-energy principle. So, this is one topic which I wanted to do very much, but I kept on deferring this topic because it's a bit tedious to do, nothing more than that. Basically derivation of the torque from the principles of energy or co-energy is a fundamental concept which is very closely related to physics of the problem, and I have been trying to follow uh, that line right from relays, actuators, synchronous machine. Of course, it is not used in transformers because it is not a rotating machine. When we are talking of torque as a function of the rate of change of angle or something like that, the synchronous machine, and then automatically the natural consequence is that it should also be done for induction machine. But if you recall, earlier I did using earlier I did torque speed characteristics of the induction machine, which is so very important. We all need to know that as electrical engineers, using a very commonly used technique which is known as principle of generalized transformer, in which one set of 3-phase windings are static, but other set of 3-phase windings are can move, and then we use the principle of we have studied 3-phase transformers, single phase transformers. Of course, single equivalent circuits are always single phase. So, we use the equivalent circuit principle to derive the torque equation and all that. But now we will again revert back to the physics and of through the method of co-energy that we have been practicing, and right at the very basic level that we are having 6 coils, 3 on the stator, 3 on the rotor, and they are mutually coupled, and the mutual some of the, because the rotor coil can rotate, some of the mutual inductances will be function of theta, and we will derive what are the flux linkages associated with these coils as step number 1. Step number 2, we will calculate what is the co-energy associated with this complete system of induction machine, and then we will take a rate of partial derivative of the co-energy with respect to the rotation angle theta, and derive a torque expression and show that it comes out to be a non-pulsating value, a constant non-pulsating value for a 3-phase machine. I think we have probably done 2-phase machine for induction. We didn't do, we did it for synchronous machine. So, we had done earlier a graduation of energy co-energy principle based upon relays actuators, which was more like single phase kind of a system, if you would like to call it that way. Then we graduated to 2-phase synchronous machine, then 3-phase synchronous machine which had 4 coils, and now today as we are going to do 6 coils in total, mutually coupled 6 coils. So, that is going to be lot of algebra, a bit tedious but fun. Let us see. I have here uh, I have here so I have drawn this figure here, In this figure, the outer limb is represents a stator. So, maybe what I can do is I can put one more winding here, but I would like to put it in a light color. So, and let me close this circle and reduce its size. Okay, fine. Let me also shade this. Same shade, let me use. Okay, so this is my stator, all right, and if I use the same shade here, if I use the same shade here, this one is the rotor. This is going to rotate usually in the anti-clockwise direction. This one is the stator, and this one here is the air gap. Air gap should be small, ideally speaking. Air gap should be small, but in my case, because of my drawing limitations, you may say that my air gap turns out to be a bit larger. But air gap is essentially required because rotation requires that the two sides should not touch. Other than that, there is no really any need other than mechanical limitations to choose a smaller to have some limited air gap. Okay, done. So, you have a stator, you have a rotor, and you can think that these coils extend like this if you want to think. This is not a, I will just use this to think of it that it extends like this somewhere on the back. So, that extended length is this L which I have shown here, and somewhere here the average radius, the gap is actually very small with respect to the radius. So, you can take a center line and that gives you the radius L. Everything should be in meters, and of course, it could be 10 to the power few is 10 to the power minus 3 meter and all that. This here the air gap is G. So, the geometry is described here. The stator has per phase ns number of turns. It is not ns by 2 number of turns, it is ns number of turns, and you know they are distributed, though shown here as very compact kind of a winding, they are distributed. The rotor is having nr number of turns per phase, and then if you look at, so this is red line indicates the A phase, the current here enters from here, it goes down, travels from below, again comes up, comes out from this dotted terminal. So, the current enters from the cross terminal and comes out from the this thing outside terminal. IA indicates that it is A phase, S indicates that it is a stator winding. So, this stator winding usually will have two components. One is the mutual component, which means it traverses through the air gap, that is usually called as the mutual component. The other is one which just sort of circles here around, but does not travel through. So, we do not have a formula for this, that is called leakage. We do not have here right now a formula for the leakage, but for the paths in which if this is the axis of the A phase winding, these are the two dots, the flux lines would, and it's distributed, and the flux lines will go like this and then they will go like this, and we have done this kind of expression derivation earlier. It is basically the same expression, because the for a two pole machine three phase winding, whether it is synchronous or a induction machine, they are not really different. So, this M indicates the mutual here, it is not actually mutual, the one which is passing through the air gap and therefore plays a very significant role in the subsequent developments that we do. That is called as LMS, will be Ns square by 4 mu 0 pi RL. So, mu 0 pi is what? I mean, it is related to the circumference, and L is related to length. So, if you elongate along the circumference and look at the length, it tells you that you are looking at the area of cross section, but because the flux densities in a distributed winding are sinusoidally distributed in space. So, it is not a constant, it is not just one flux density multiplied by something. So, therefore, it does not come as just 2 pi RL, but just comes as pi RL by 4, which is the number Ns by 2 whole square. So, that comes as 4, and inductance is inversely proportional to the length of the air gap. So, the G comes down, again actual length of the air gap is 2G. So, you all those factors have adjusted and become here by 4, and so mu 0, you can go back to the synchronous machine or the rotating MMF machine concepts, 3 phase rotating MMF machine concepts, and look at this derivation there. The LMS comes out to be Ns by 2 whole square mu 0 pi RL by G. So, this is the inductance of A phase winding. Now, similarly 120 degrees ahead, you have a dot here, because this is dot here, this is my positive direction of rotation. So, the B phase or the Y phase, it is RYB or ABC. So, the B phase winding here. So, while drawing I draw it as RYB, while writing usually I prefer ABC. So, the B phase winding here, like the same dot, I have shown here also the same dot, because 120 degrees in space and 120 degrees T by 3 time period later, this is how it will look like when it is carrying its peak current. These dots are, if these dots represent when the currents which are sinusoidal in nature, which are pushed through these windings are at peak value, then you can imagine that this is the picture corresponding to when the currents would have peaked here, which will be T by 3. If it is a 50 hertz machine, then the time period is 20 millisecond, and 1/3 of the time period would be 20 by 3 or so millisecond. At that time, this would be a dot, that is the current is entering here, and current is entering here at the cross and exiting here at the dot. Just like here, the current was exiting at the dot and was entering at the cross. And then, so this span is this span is 90, this is 30, so this is 60. Another 60 degrees down, you will mark the dot of the B phase winding, and opposite, diametrically opposite to it, you would mark the cross of the B phase, the C phase winding, the color being blue, but the nomenclature being C phase. So, R is mapped to A phase, Y is mapped to B phase, and color B is mapped to C phase. Maybe I can just, instead of writing it like this, I can just indicate on this. The red color is mapped to A phase, the yellow color is mapped to B nomenclature, and the blue color is mapped to C nomenclature. Okay. Now, this covers the 3-phase winding on the stator. Now, similar 3-phase windings are there for a 2-pole machine, induction machine, and the 2-pole induction machine, the rotor at synchronous speed will rotate at 50 hertz, which is corresponding to 3000 rpm per minute. Now, for this, similar windings exist with different number of turns, and we are using the same R. Actually, the R should be a bit different, but because the gap is very small and the dimensions are large, so therefore, we are using the same R here, and mu 0 pi R L by G, same again formula recurs. Just look at this, that at this snapshot where we have drawn it, it is theta degrees rotated, it's rotated by theta degrees in the positive anti-clockwise direction. So, the corresponding conductor to this, the corresponding conductor is theta degrees later. So, if this is right now the axis of the A phase winding of the stator, then the axis of the A phase winding of the rotor is like this. And once you have marked this, diametrically opposite comes this term, then go 120 degrees on the rotor circumference further, you get the yellow colored windings, and then from here you go another 120 degrees and you get the B colored windings or the ABC windings of the rotor. Now, these windings, suppose the theta is 0, that means these winding, this is perfectly here, this is perfectly here, then you can talk of the, at that time, the mutual inductance between the A phase of the stator and the mutual inductance between the A phase of the rotor would be at its maximum value. And what would that be? This constant in that case will not change, right, because the geometry is same, the air gap is same, the magnetic axes are properly aligned. So, only thing that is going to happen is you will get product of the number of turns on the stator ns into product of the number of turns on the rotor nr by 4 mu 0 pi rl by g. So, this is what you will get. Now, I have 6 flux linkages to worry about. A phase stator, flux linkage associated with the B phase winding of the stator, flux linkage associated with the C phase winding of the stator. A phase of the rotor, flux linkage with the B phase of the rotor, flux linkage with the C phase of the rotor. Now, this will be a function of the current in its own phase and the corresponding inductance term that will come is corresponding to the self inductance and also in this case the stator inductance. So, Ls, then see the A phase coils are stationary, so you have mutual coupling between A phase and B phase windings of the A phase and B phase windings of the stator and A phase and C phase winding of the stator. So, those are the next two terms, and again we have derived it earlier that this will be cos, it reduces, we have seen that if the angle between the two axes of the two coils is theta and some peak value is some A, then if the angle between the axes become theta, then the mutual inductance will become A cos theta. So, that all derivation was also done some time back. So, if the angle between the two coils is 120 degree, cos of 120 degree is minus 1 by 2. So, therefore, this will become minus of LMS by 2. So, A phase flux linkage associated, A phase flux linkage is associated with the stator winding will be, first term will be contribution due to its own self inductance. Second term here is minus of LMS by 2, which is the mutual inductance between the A phase and the B phase winding of the stator times the current in the B phase of the stator winding. Then the mutual inductance between, this is MAC, mutual inductance between the A phase and the C phase of the stator winding, which is same by symmetry of the 120 degree symmetry of the geometry of this thing. All self inductances are identical, all mutual inductances are identical. The situation becomes a bit rough or complicated when you have this theta angle coming into picture when between stator and rotor, but here with just the 3 phase windings on the stator, or if you consider 3 phase winding just on the rotor, the situation is not at all complicated. So, the third term is minus MAC of the stator, which is minus LMS by 2 times the C phase current in the stator. So, now all the contributions to the flux linkage of the A phase of the stator due to the 3 windings of the stator are taken care of, but you have to still additionally consider the 3 windings which are there on the rotor, the A phase, the B phase and the C phase winding, and they are carrying current IAR, BAR, IBR and ICR. Now, see this M, if the A phase winding of the rotor and A phase winding of the stator were perfectly aligned, theta was 0, then the mutual coupling between them would have been this value. But if the rotor winding has moved by theta degrees, then what will happen to this? This number will become m cos theta. So, therefore, the mutual inductance between A phase of the stator and A phase of the rotor is m cos theta times the rotor current IAR, the current in the rotor A phase winding. So, the fourth term which contributes to the flux linkage associated with the stator is given by this particular product. Now, the next question will come, what is the mutual inductance between A phase winding of the stator and B phase winding or the yellow color winding of the rotor? So, you take exactly the corresponding conductors, that is what we have marked here. You exactly take the corresponding conductors here and measure the angle. So, this and this, these are exactly identical, but they are on the stator. So, this angle is 120 degrees, and then since the rotor has moved by 30 degrees, just like between A of stator and A of rotor angle is theta, similarly between the B of stator and the corresponding conductor B of rotor, an angle of theta has happened. So, between B of stator and A of stator 120 degrees, additional 30 degrees here. So, therefore, the how much did it became? 120 plus 30 theta, it became 120 plus theta. So, that term here we have written m cos theta plus 2 pi by 3. Let me write it more clearly. M cos theta plus 2 pi by 3, maybe I can expand it a bit. Okay. And so how did we, again I just repeat once and then I move on. How did I get this theta plus 2 pi by 3? By comparing this conductor, this conductor is fixed, this conductor is fixed, corresponding conductor of the B phase winding of the rotor I took, and I measured this angle and this angle, which came out to be theta plus 2 pi by 3, because this angle was 120 and then additional theta was added. So, m cos theta plus 2 pi by 3, and then for the last this mutual inductance is between A s, BR. So, it has to be multiplied by the current IBR for the mutual. So, this current will multiply with this, and then automatically the last conductor on the rotor of the C phase will now be at an angle of theta minus 120 degree, because this whole thing has moved by theta. So, in the theta equal to 0, angle between this and this would have been 120 degree, but because it has moved by theta, it has reduced and has become theta minus 2 pi by 3. So, the corresponding mutual term will become m cos of theta minus 2 pi by 3, m cos of theta minus of 2 pi by 3, which is what I have written here, and this is between AS and CR. So, the current with which it should be multiplied is ICR. Now, we know first row is first complete row is explained. Even this block I had fully explained. Now, let us look at B of S. This part is already explained, because it is a very simple symmetric structure. Mutual inductance between AS and BS times current into of AS, self inductance multiplied by its own current, mutual inductance between BS and CS multiplied by, this is the mutual inductance multiplied by the current in the C phase winding. This is done. Now, to explain this, the third term, you can again do the same thing looking at the geometry very step by step, or what you can do is, you can start from the always the self inductance term and proceed cyclically and write your terms by closing the cycle. So, this was m cos theta in 1 location. So, now in 2 location it has become m cos theta. The next term, the next subsequent term in the column was m cos theta plus 2 pi by 3. So, I can write here m cos theta plus 2 pi by 3 following the cyclic order, and then the last term here will circle back and come here. So, the last term here circles back and comes here as the first term, which is m cos theta minus 2 pi by 3. And then for the C phase, we first fix the self inductance term, because it is easy to fix that, because it is in the diagonal. So, that is m cos theta. Then the very next term should be m cos theta by 3. So, we circle around, it will come to the first position. So, therefore, this term now moves here and this term moves here. So, in a nutshell, all these terms have been explained to you. Now, in the let us first look at the mutual coupling matrix between the just the 3 windings of the rotor. Whether the rotor rotates or it does not rotate, it does not matter. The 3 windings on the rotor are stationary relative to each other. So, they behave very similar to the way your 3 windings of the stator behave with respect to each other. So, the self inductance of the 3 they come on the diagonal LR, LR, LR. The mutual, because always the angle between the B phase and the C phase windings with respect to the A phase winding on the rotor is 120 degree. So, therefore, minus LMR by 2 minus LMR by 2, and so this is exactly the same structure is repeated here, but with the S subscript replaced by R subscript, which means the corresponding mutual inductances would be replaced like this. And now, the last thing I know, that for a linear circuit the mutual inductance is when you write it in a matrix form, the matrix is going to be symmetric. So, therefore, whatever is here, the transpose of this should come here. because when I take transpose of this whole matrix, it should turn out to be a symmetric matrix. So, this will become its own transpose, which is actually the same, because this whole diagonal matrix itself is symmetric. This diagonal matrix will also, subdiagonal matrix will also become 2 cross 2 block, if you want to say 3 cross 3 block more correctly. This its own transpose is again the same, because it is already seen to be symmetric. If this is written as MR transpose, then when I take transpose and bring it here, it will become MR, which is what is written here. So, therefore, from the notion that this matrix has to be symmetric, I can write this as MR transpose. Now, this becomes a 6 cross 1 vector, this becomes a 6 cross 1 vector, and the coupling matrix becomes the 6 cross 6 matrix. So, our first step number 0, calculate all the inductances using geometry, we did. Step number 1, write the lambda I flux linkage equations, and because you have 6 windings, it is better to write not plain equations, but write them as a matrix, in the matrix form, with the vector corresponding to the flux linkages, vector corresponding to the current, and intervening matrix, which is the 6 cross 6 inductance matrix. So, the inductance matrix is also written, means we have written lambda as vector is equal to a inductance matrix L times the current I. This task is also done. Now, let us come to the next step. So, step 0 done, step 1 done. Now, what is the step 2? Step 2 is calculate the co-energy of this system. Now, to calculate the co-energy of the system, knowing the fact that they are path independent, we can choose any our appropriate path. We will follow the same standard notion that we did earlier. First, let the whole system be unenergized. We want the co-energy of the system when the currents in the stator are IA, IB, IC, S indicating the stator, and current in the rotors are AR, IBR, ICR, which just succinctly I call it as IB, IA, IB, ICR, and the seventh, so 6 variables, state variables, and the seventh state variable is theta, the angle of rotation of the axis of the A phase winding with respect from between stator and rotor, or the corresponding two conductors of the stator and the rotor. So, that becomes theta. So, we get 7 state variables. Initially, we will just rotate it by, keep everything energized and rotate it by an angle theta. Work done is there 0. So, that term need not be put into picture at all, and then afterwards we start accumulating, that is we start first in look at what is co-energy, basically lambda times of di integral of this. So, what we do is we use a dummy variable, this dash is indicates a dummy variable. So, for the lambda AS, A phase stator flux linkage, which is a function of all these 6 things, and theta is already set to its final value. The current in the A phase will be increased, which is shown by the dummy variable IA dash. It will be increased from 0 to whatever value you want, IAS, while all the other currents will be maintained to 0. So, this will set the first term of the corresponding to lambda AS. Now, after that we will calculate the co-energy associated with the B phase winding. Now, A phase current theta has already reached its final position. We are going step by step. A phase current has already reached its final value. So, this so the IA has reached, IAS has reached its final value, IAS has reached its final value, and now the IBS current will be increased from 0 to IBS. Everywhere while showing, I show the dummy variable by dash. So, it is increased from 0 to IBS, and still I am not going to, I am one by one I am energizing the coils. So, therefore, the third, all the other remaining currents remain 0, and this will give me the flux linkage associated with the integral of flux linkage times the current of the B phase winding. And then when I come to the C phase stator winding, these two currents are set, already reached their desired value. C phase stator winding current will now be increased, the C phase stator winding current will now be increased from 0 to this value, and this third term will result, the other currents are still 0. And then we go to the fourth term. Now, all the three windings on the stator have been excited. Now, we have to excite the three windings on the rotor step by step again. First, increase the IAR current from 0 to its IAR value. So, use the dummy variable IAR dash, use it in the integration. Limits of the integration are set from 0 to IAR. First three stator winding currents have already reached their respective values, and the B phase and the C phase rotor currents are still set to remain at 0. Calculate this term, then come to the lambda Br, then come to lambda Br of the rotor. So, again now these three currents on the stator are at their correct value. The A phase rotor current is also at its appropriate correct value, and increase the B phase rotor current from 0 to its desired value IBR, and complete this integration. And then last, with all these 5 now set to their respective values, all these 5 set to their respective values, increase CR, the current in the C phase winding, from 0 to ICR, and complete this integration by using this dummy variable ICR dash, and that will give you the co-energy Wm dash. Dash indicates here not the dummy variable. On this, Wm is the energy, magnetic field energy, Wm dash is the co-energy, which basically, if you remember, was for a single coil defined as lambda I minus omega, and then that definition was extended to. So, now let us finish off. The next step would be to write each of these integrals. So, the first integral is very simple, because all other coils are carrying 0 and only my own coil A phase stator is carrying a current I, and the lambda is lambda AS so the lambda AS is just LS into IAS, no other term is there, and then integrated this d I dash from 0 to IAS. So, in this will LS taken constant, this will become half of I square, and so on. This we have done earlier. So, this there is just one term corresponding to the self inductance. So, the energy stored will come out to be half of LS IAS square. So, this term, because no other term, no other coil was excited, is only the energy stored in its own self inductance, which is half of LS IAS square. Then when I come to this second term, I will get two energies. Which are the two energies? One, or rather co-energies, but terms, one corresponding to the self inductance, and so that would be half of Ls IBS square, and one corresponding to one corresponding to this this will gives me half of Ls IBS square, and the other is, I will write it here, minus LMS by 2 times IAS. This current is already fixed, right? When I am doing this, the A phase current is already fixed. So, there is nothing to worry about this, and then what is changed is only the, so this times, this is being integrated, this actually what you are doing is you are first writing this as Ls, okay, I am sorry, let me properly, minus LMS by 2 IAS plus LS IBS dash, and then this term is being integrated from 0 to IBS times DIBS dash. So, when you do this, whole of this thing is like a constant, and then take it out. So, integral of 1 times of dBs of this will just be IBS S dash, and limit of integral is 0 to IBS. So, therefore, this term will just come out to be minus LMS by 2 IAS IBS, which is the term which is shown here, and the second term when you integrate, that term will come out to be, this is something like Lx dx integration from 0 to some x naught, which is half of Lx square. So, this second term will come out to be half of Ls IBS square, and then the third, so because only two currents were active here, there is no contribution, because all the remaining mutual currents associated with the mutual inductances were 0. So, no other term comes here. So, first one gives you only one term, second one gives you only two term. Then you come to the third equation, third expression in this coenergy expression, which is the flux linkage associated with the C phase winding. So, in that case you will have a term which corresponds to the self inductance of the C phase winding of the stator. So, this is what it is, and because the A phase currents and the B phase currents have reached their respective designated values. So, therefore, you will have two terms which are coming from them. So, with respect to, now you can just you can use the common sense now, that some common sense has been developed. You can write this as IAS CS between C and A phase. So, the product of the those two currents and the mutual coupling, which is minus Ls by 2, exactly following this thing here, and then mutual coupling between the B phase and the C phase of the stator, product multiplied by minus LMS by 2. So, we explained all these three terms, we explained this, we explained this, and with respect to the rotor, still now no contribution came, because the rotor currents until this step is over, the third integration is over, the rotor currents are set to 0. Then in the fourth step, when I am calculating the integral with respect to lambda AR times d I AR, at that time 4 terms will come, because now I am increasing the current in the A phase winding of the rotor. This is just a mathematical manipulation from 0 to its designated value. While I am doing that, the currents in the A phase, B phase and C phase, current in the A phase, B phase and C phase of the stator winding are actually at their designated values. So, because they are at their designated values, they are carrying their flux linkage, and this current will interact with them, and a stored energy component will be created, exactly following the same lines. So, the first term will correspond to the self inductance, which is half of Lr IAR square. Now, with respect to A phase, of the rotor and the A phase of the stator. The mutual inductance is m cos theta. It's here, it's here m cos theta. It should be multiplied by, this mutual inductance should be multiplied by the two currents of the respective winding. So, IAS and IAR, and similarly the mutual inductance of the uh, so which row am I looking? I am looking at the fourth row. I am looking at this equation, right. So, I have to I do not still need to worry about these two last terms because these currents are 0. So, I need to worry about these 4 terms, of which this term I have already accounted. Now, these first 3 terms which of the fourth row are nothing but the first 3 terms of the fourth column, is it not? So, the first term was m cos theta, then what would be the next term? The next term will be m cos theta minus 2 pi by 3. So, m cos theta minus of 2 pi by 3 into IB of the stator times IAR of the rotor. First IAS of the stator, IAR of the rotor, then IBS of the stator and IBAR of the rotor. And then the third term would be m cos of theta, this is the term sitting here in this. So, it should be multiplied by which current? ICS, and the term is m cos of theta plus 2 pi by 3. That is why I wrote everything down first and brought it, because if I do it live I can myself make mistakes. M cos theta plus 2 pi by 3 ICS into IAR. So, all these 4 terms corresponding to the integration here is now explained. Now, we have to take here, and now you can see there will be 5 terms which are involved, and for those 5 terms the for those 5 terms the last 2 terms come from here, the self inductance term and the mutual inductance with respect to the winding, other winding on the rotor, which is the A phase winding on the rotor. So, those are fixed inductances, and Lm minus Lm bar by 2 and Lr, and these are the 2 terms. And then so I am moving in this direction, then I have to look at these 3 terms. To look at these 3 terms, basically I have to look at these 3 terms, because this is transpose of this. So, this fifth row first 3 terms are the first 3 terms of the fifth column, and picking it from there I write it down as this. So, I write it down. First term will be m cos of theta plus 2 pi by 3 IAS IBR. Next will be m cos theta, which is the diagonal term. So, the m cos theta IBS IBR, and then the remaining will be m cos of theta minus 2 pi by 3 ICS into IBR. And then we come in this, I said this is a bit tedious, this last term lambda CR, the flux linkage. So, all the 6 currents will now come into picture. So, I have 1, 2, 3, 4, 5, 6, I have all the 6 terms here. Again these first 3 terms are just very similar, last 3 terms are just very similar to the corresponding C phase flux linkage term for earlier we had derived for the stator, except that the S is replaced by R, and then the only really speaking interesting terms which need explanation are this, but these are again you can explain them from this column here. These 3 terms are the, what are the these 3 terms sitting here, and so the with IA you will get a IAS, you will get a term corresponding to theta minus 2 pi by 3. With BS you will get a term corresponding to theta plus 2 pi by 3, and diagonal will come as m cos theta between, it is not exactly a diagonal, but between C and C of S and R. And so, this whole thing will become, give me the summation of whole of these terms here. So, 1 plus 2 plus 3 plus 4 plus 5 plus 6 arithmetic progression will give me W m dash. And once I have calculated that, then what should be my next task? My next task should be to take its partial derivative with respect to theta. So, before doing that, what I will make 2 points. See, is there any theta term coming here? No. So, there will not be any partial derivative with respect to this. Is there any theta term coming here? No. So, there will not be any partial derivative with this. Is there any theta term coming here in this? There is no theta term coming here. So, no partial derivative with respect to theta. So, where theta does not come, we can just ignore it. Similarly, this sub block also does not have any partial derivative with respect to theta. So, this also can be ignored. So, now only I have to take d by d theta of the summation of only this much, d by d theta of this particular summation, only this I have to consider. So, what I will do is, I will first group these terms. If I go like this, what do I see? I see that IAS is common. So, I take IAS common, then I write m cos theta times of IAR, m cos theta times of IAR. Next is m cos theta by plus 2 pi by 3 into IBR, m cos theta minus 2 pi by 3 into ICR. So, I take these three summation taking IAS as common, and then this partial derivative with respect to theta, this is what I am taking. And then similarly, in these three terms I take IBS common, and then write the remaining terms as m cos theta minus 2 pi by 3 into IAR plus m cos theta into IBR plus m cos theta plus 2 pi by 3 into ICR. And then finally, coming here again I take ICS as common, and partial derivative with respect to theta of the summation of these three terms, which I have written it here. Now, what are these three things? Basically, if you look at this very carefully, we will anyway simplify it, but what is this three thing? So, this is basically the flux linkage between the stator and the rotor of A phase. So, IA means the current in the IAR, IBR and ICR, the three currents in the three phase windings of the rotor. How much flux linkage are they creating in the A phase of the stator? This is what is described here, because these terms are coming from where? These terms are coming from here. So, therefore, this is nothing but, this is where am I? Yeah. So, this is nothing but partial derivative of the flux linkage of A phase of the stator due to currents in the three phase currents in the rotor. Similarly, the next two terms are flux IBS times the flux partial derivative of the flux linkage in the B phase of the stator due to three phase currents in the rotor, and the third term is also for the C phase is similarly written. So, succinctly this whole thing can be written like this. Now, we just need to simplify these three terms, we need to just simplify these three terms. Now, our work is becoming easier, minute by minute it is becoming easier. So, suppose that the three phase rotor currents are given by IMR cos of omega r t plus beta, where what is omega r? Omega r is the rotation frequency of the voltage in rotor, and you if that is omega r and speed of the motor is omega m, you know that omega r plus omega m is omega s. That means, if the machine is rotating with omega m speed, synchronous speed is omega s, the difference of the two is omega r. This much extra frequency voltages have to be induced in the rotor. This we have discussed earlier. So, that same omega r is used here. Beta is to show that we can fix cos omega st or one reference phasor, then the other things are relative to that. So, beta comes from there, and that would be the stator winding A phase, that would be our reference, and then by the 3 phase balanced operation, B phase current lags by minus 2 pi by 3 radians, and the AC phase current leads by plus 2 pi by 3 radians. Now, substitute this for this, substitute this for this, these 3 currents, substitute this for here, m cos theta IAR, m cos of theta plus 2 pi by 3 IBR, m cos of theta ICR, substitute these currents. So, m times of IMR, the m indicates here magnitude, r indicates the rotor, this is taken care of. Then comes cos theta into this only this cosine term I need to write here. So, it becomes cos of theta into cos of omega r t plus beta. Then comes the cos of theta plus 2 pi by 3, cos of theta plus 2 pi by 3, this m should not have been here. So, I am sorry, this I miss, these 2 m's are not there. Yeah. So, I get cos of theta plus 2 pi by 3 term coming from here times IBR, which is cos of omega r t plus beta minus 2 pi by 3, and then the third mutual inductance term gives the contribution of cos of theta minus 2 pi by 3, and the corresponding current term comes as omega r t plus beta plus 2 pi by 3. So, now one interesting thing you see here that is happening is this term here with plus 2 pi by 3 is associating with another term of minus 2 pi by 3. Similarly, here another term minus 2 pi by 3 term is associating with the plus term of plus 2 pi by 3. So, in general, if I say, if I write x is equal to theta and I write omega r t plus beta as some y, then the first term is cos x cos y, then this next term is cos x plus 2 pi by 3 and cos y minus 2 pi by 3, and then the third term is cos x minus 2 pi by 3, and the last here is cos x cos of y, this is y plus of 2 pi by 3. So, this is the summation, and if you look at cos x cos y plus this summation, you can show that it expands to 3 by 2 cos of x plus y. How? Because 2 cos x cos y will be half of cos of x plus y plus half of cos of x minus y. Then this, when you write 2 cos a cos b, half of x plus y would give you, when you add the a plus b, when you add these two things, this and this will cancel. So, you will only get x plus y, and when you look at a minus b, then this minus 2 pi by 3 will become positive, add with this 2 pi by 3. So, you will get it as x minus y plus of 4 pi by 3, and similarly for the third term, when you add a plus b, this is what is a plus b, and when you do a minus b, this is what is a minus b. So, these 3 terms are constant, they add together and give you 3 by 2 cos of x plus y, but these 3 terms are same angles 120 degree apart. So, if you do their summation, they will turn out to be 0. So, therefore, this whole summation is going to be to be equal to this 3 by 2 of 3 by 2 of this, and now substitute for theta x as theta, and for y substitute it as um, omega r t plus beta. So, you get that your lambda mutual linkage in the flux mutual flux due to rotor currents in the A phase stator, that is given to you as 3 by 2 m I r, because your m was common here already, this term was taken as common, and the current was I m r cos of theta plus omega r t plus beta, and then I can write by similarity subtract minus 2 pi by 3, and yeah. So, before doing that, now what is it before going to B phase, what is the next step that I have to do? I have to take partial derivative with respect to theta. So, I take the partial derivative of this with respect to the theta. So, the cos becomes minus sine m I r sine of theta plus omega r t plus beta. So, this is all this is what I get, but what is theta? Theta is some omega m of t plus some initial angle alpha, but when I add, so when I add to this omega r of t, then omega m plus omega r will become omega s. So, therefore, this whole thing will turn out to be just omega s of t plus of alpha, and this beta is already sitting here. So, this beta will come here, and therefore, I will get this partial derivative as minus of 3 by 2 m into I m r sine of omega s of t plus beta plus alpha, and then the other two partial derivatives I can argue from symmetry principle will be lagging by another 120 and another 120 degrees. You can check it out. So, now I have simplified this term, this term, this term. I need to just substitute IAS, IBS and ICS. So, let me take IAS as IMS cos of omega s of t, IBS as IMS cos of omega s of t minus 2 pi by 3, ICS as IMS, M indicating magnitude, S indicating stator, and here omega s indicating synchronous speed, cos of omega s of t plus 2 pi by 3, and now I substitute. So, this one here, this sine term here multiplies by cos of omega s of t, then this sine term here, multiplies with the B phase stator current cos of omega s of t minus 2 pi by 3, and this one here multiplies by cos of omega s plus 2 pi by 3. So, here the grouping is exactly similar, minus 2 pi by minus 2 pi minus 2 pi by 3 plus 2 pi by 3 plus 2 pi by 3, not unlike here where the plus 2 pi by 3 and minus 2 pi by 3 were grouping. Now, if you expand this we have done it many times. So, I am not going to do it again. Basically, what will happen is you will get only that constant term which corresponds to a minus b, which is nothing but and a 3 by 2 constant will again come out common. So, therefore, it will become minus 9 by 4. The two currents IMS, IMR, M, that where does that two currents come from? These two currents come from from here and from here. IMS comes from here, IMR comes from here, mutual inductance has also come from here, and so this is explained. This minus 3 by 2, I am sorry, this minus 3 by 2, when you expand this again another 3 by 2 comes. So, this becomes minus 9 by 4, and the difference term only matters where omega st cancels out, and only this remains as sine of alpha plus beta. This is simple 2 sin A sin B equal to sin A plus B sin A minus B for each one of the 3 terms, and then you have to group them together. And these many newtons is the torque which is developed, and you can just see that it only depends upon whatever is your steady state value for alpha and beta, and a steady state torque will be developed. So, we have done that very basic physics, and the at a very basic physics level, not on the equivalent circuit level, we have shown that actually a steady state constant torque can be developed. Constant means instantaneous torque being constant can be developed without any pulsating component in a 3-phase induction machine, 2-pole 3-phase induction machine, 3 coils on the stator, 3 coils on the rotor. Doing lot of work for one day. This is the most complicated derivation that we have done. As we are about to close this course very soon, I think we are just maturing, climbing the hilltop, so to say, climbing the peak of your mountain, so to say. I think we will stop here for today. Thank you.